Today we will talk about non-parametric learning methods as some additional group of methods in machine learning, and in particular about perceptron algorithm. So in the beginning, we need to estimate and to define the difference between parametric and non-parametric algorithms. When we are talking about parametric methods, we may associate it with some assumption about probability, about distribution of probabilities inside inside our data set. So we assume that we have normal distribution, for example, and we estimate some statistics about this distribution, such as mean value, standard deviation, and something else. So as for feature discriminant analysis, we assume that we have normally distributed data, and we calculate covariance matrices and something else. So we make some assumption about distribution. But in non-parametric learning methods, we don't declare some assumptions about our data. We just working with without any statistical properties of the data set. We're working with data itself, without assumptions. So in this case, non-parametric models also has some specific characteristic, and complexity of the non-parametric models grows with the number of training sets. In parametric models, we have some fixed number of parameters. So we have some fixed structure, which has estimate some distribution, some parameters of data set, and that's all. So our linear regression, logistic regression, and linear support vector machines is a parametric learners. Yes. So for example, in linear regression, we calculate B0 and B1 coefficients, yes, using simple expression, yes. And it does not, calculation complexity does not depends on number of data set. And we have some weight coefficients in this case. But k-nearest neighbor classifier, decision trees, and some support vector machines with specific kernels. When we estimate distances between objects, it's non-parametric learning algorithms. And as for decision trees, you may just intuitive way to understand that when we create some decision tree with rules, so for example, if parameter less than some threshold, it will be our class 1. If parameter greater than threshold, it will be group B. So in this case, complexity of this tree depends on data set, and also it means that we will work with non-parametric model. So, but I want you to fix in your memory the main idea that in parametric learning algorithms, we make some assumptions about distribution of the data set of parameters. In non-parametric, we just deal with the data without any assumptions about distribution. Let's start with Perceptron algorithm. It's the most popular non-parametric methods, and Perceptron is an artificial neuron, and it's also using in neural networks theory. So we have some input vectors X, and they are represented as vector Y with some features from 1 to n. And also we have additional column here, or additional parameter, which will be equal to 1. It may be the first element or last element, it doesn't matter. So in this representation of our input vector, we have similar elements between 1 and n, and some additional elements 1. This element allows us to add to our expression some B0 coefficient. So without multiplication to parameter of the vector from meaningful columns. And you know that separating surface may be expressed using this equation when we calculate the sum of multiplied weight vector to our parameter, and it should be equal to 0. So separation line expressed by this equation in matrix form, it will be like this. You've seen it when we've talked about feature discriminant analysis. And when we have classes gamma
Theta.
1 and gamma 2, it's gamma sign. I don't remember actually.
No, sorry, this is theta.
I think that yours, yes. I think that it's gamma.
It's Greek. It's their letters.
And it means, and let's assume that these two classes has linear separability, so we may create this surface to separate classes. It means that the weight vector W should satisfy these two expressions. For all classes, for all objects from the first class, projection of our vector to weight vector should be greater than 0. For all objects from the second class, this projection should be less than 0. So it means that all objects from the first class lies in the positive part of our space, and all objects from the second class lies in the negative part of the space. With such a representation, a two-class classifier can be depicted as shown in the next slide. Over here, I will explain it a little bit later. And it's a perceptron, actually. The projection greater, it will be first class, less, it will be second class. And learning such a classifier on the Lorentz sets gamma implies the choice of the vector components. So what does it mean? We need to learn our classifier. We need to define all our coefficients, and number of coefficients will be n plus 1, because n plus 1 is like a free coefficient. So if you have 10 features, it means that you will obtain 11 coefficients. So that presenting any object from the first class at the input would produce plus 1 at the output. So this vector should give a projection of the object to this vector should produce plus 1 for all objects from the first class and minus 1 from the for all objects from the second class. So it's our aim to find this weight vector. Let's look to an example. We have some object y, and we have some perpendicular to this object plane. In the right part, you have positive projection. In the left part, you have negative projection. And for you see that our logical unit response depends on the point our vector position relative to the object plane is shown above. So if you have weight vector like this, you have positive projection of the weight vector if your weight vector lies in this field, you will obtain positive projection. If you have a weight vector here, you will obtain negative projection. So this vector is not so good as this one. As you remember, projection calculates as result of multiplication of vectors lengths to cosine of angle between between two vectors. And this is our algorithm. When we have input values, I forgot to add to this table last column with ones. So also here will be additional column with ones. We have our observation, we have weights, and we have some summaring and comparison with zero, logical threshold you need. And the output we will obtain plus or minus one, some answer, sign of the response. If all samples of the second class are multiplied by one, then for training purposes, the equation take the following form. So all projections should be greater than zero for each elements for both classes, 1 and 2. If you see, in this case, we have two equations, but if you multiply all classes, all elements from the class 2 to minus 1, we will transform our equation into this form. So training objects from the dataset Y are presented in sequence Y1 and the weight vector W. So we just select the first object and we change the weight vector Y several times, and times of the number of steps corresponds to the number of objects. And after the object from our class appears, and this rule is satisfied. Where is it going? So our weight vector does not change, so it remains permanent. If we obtain results less than zero, so we need to recalculate position of our weight vector, and we are just transfer it into new position using this equation. Our update vector will be calculated as our previous vector plus some correction c multiplied by object, where c is compensation factor, its ordinary coefficient number, and objects are presented as a periodic or at random order, so until the results are repeated for each of them. So you just do it. If you have 10 objects, you do it 10 times. And the initial value of weight vector selected randomly, you just select some weights, you initiate your weights randomly. And after that, I need to calculate for each object this equation and compare with zero. If it's greater than zero, so you don't do anything. You don't do anything with your weight vector and select next object. If you have result less than zero, you correct position of your weight vector in order to find the position of the weight vector for which all projection will be positive. So we consider and it will be sequential learning with error correction. We consider the procedure of sequential learning when the learning objects are presented sequentially, so one by one, and the vector weight vector y is adjusted with each new input vector y. If the object satisfy expression is left unchanged. W vector is left unchanged, so you don't move your weight vector. In contrary, you need to correct your weight vector with correction factor. So in this case, you have. Let's look to the picture. I'll just take some pen. We have some observation. In this case, it's ith object, and we have some weight vector W. In this case, when we project this separation hyperplane is perpendicular to our, it's always perpendicular to observation, because it divides our surface into two parts, where we obtain positive projection. Here projection will be equal to 0, and here will be negative projection of our vector. So in this part of the space, projection of the weight vector to projection of object to the weight vector will be less than 0. It means that we need to move our weight vector in such a way which provides us positive projection. So we just move our weight vector to some angle in direction. So we move it closely to the observation, and this vector will be some coefficient multiplied by the observation. You see that we have two perpendicular vectors here. This one and this one, they are perpendicular one to another. And also you need, I think that you remember that when we have two vectors like this, some of these two vectors will be here. A, B, and A plus B. So in this case, you transfer your weight vector, you correct your weight vector in order to obtain positive projection. So, and you repeat it with all objects from your data set. Is it clear? Could you just say some words, or I need to repeat it one more time?
For me, everything's clear.
You may write to the chat plus, minus, or plus, minus. How do you understand this material? Because I hear only silence. I don't understand. Do you hear me actually?
No, I wanted to ask you, because you said that the y and the direction we moved the negative projection, the old W.
And what about other students?
I'm sorry, can you hear me?
Benedict, Hassan,
Ah,
Fidel, okay. Steven, Zineb. I'm talking about plus minus. Okay, let's repeat it one more time.
I'm sorry, can you hear me now?
Oh, I turned off my microphone, so my volume, so maybe I didn't hear you. Just sorry.
So you can hear me now?
Now, yes.
Because I've been talking for some time. I just wanted to ask you about the Y. I was asked to comment that Y and the direction we moved the old W. You said they're perpendicular.
Perpendicular our separation surface, our surface which correspond to observation. So this is perpendicular will be
Surface. Yes.
Yes.
Yes, I understand. Thank you.
So this surface will be perpendicular. It's like a decision surface, which divide our space into positive part and negative parts. And perpendicular will be after all, perpendicular to weight vector surface will be after all corrections. So when we as the result of calculations, we obtain weight vector and surface which is perpendicular to this finished version of the weight vector will be our separation surface. But in this process, it's not. We don't look to separation surface again. And one more time. Mhm.
How can we decide the value of the angle we should rotate the old vector?
This parameter C, which is correction factor, just select randomly by your own. It's like a hyperparameter of the model, which you need to estimate just experimentally. Yes. So you just this correction depends only on C value, nothing special. So just transfer weight vector in direction of y.
Yes. So it's completely arbitrary. It's not some specific, or there's no rule for the value of C.
For this type of algorithm, no, but we will look to some modification of this algorithm when this parameter may be calculated in some specific form. So there is some variant to calculate it, to estimate it, and we will talk about it a little bit later today.
Thank you.
So, and I just repeat it one more time for Fidel. So Fidel is for you. We have some vector of our object. So our object in multidimensional feature space is a vector yi. We have some weight vector which we assume that allows us to calculate to which class our object belongs to. And we want to correct this weight vector in such a way which gives us more accurate prediction. So we know that we have to transfer our weight vector in the way which produces positive projection of the observation y to the weight vector. So we just move our weight vector. It will be updated vector w with upper sign, upper comma, which is equal to our original weight vector plus correction. So, and we do it several times with all elements in our data set. So we just take new y, next y, calculate projection. If it's greater than 0, we just take the next observation. If it's less than 0, we correct our weight vector and go to the next element and do it again and again. In ideal situation, for all our observation, for all our y's, we will have positive projections, but in real life, it's impossible. So there are several modifications of the algorithm. Algorithm with a constant coefficient. When our coefficient C is equal to some constant value, for example, 1, we just we just move our weight vector in the way which is just calculate the sum of the weight vector and our object. We are trying to move it closely to our vector of object. As you see in this slide, it doesn't mean that we will have positive results after this correction. In this case, our update vector does not improve the results because we have and also for corrected vector we have negative projection. You see that this new vector lies in the negative part of the plane. So it means that we need to choose more, that we need to choose C greater than 1. Yes. The next variant of an algorithm is algorithm with absolute correction. This algorithm, the coefficient C is choosing and U at each step of object while presenting. So it's not constant for all data set, but it changes. And the value of C being taken as a least integer that makes our projection greater than 0. That is, it's chosen subject to the condition. So we need to find the minimum integer C value, which allows us to obtain positive projection. And this is quite logical way to find the C. You take C equal to 1, C equal to 2, C equal to 3, and calculate results of projection because in this case you obtain, for example, in the previous case we have the same situation. You see that in this case C is equal to 1 is not enough for us, yes, because we did not cross our line. But in this case, when C is equal to, I don't know, to 2, maybe it will be better because when it was 1, it's not enough. So, and you need to calculate this in order to estimate C also greater than. Also, you may see some explanation how to estimate the C value. So C should be the least integer greater than this expression, where we need to calculate the value of projection to our original weight vector and length of this vector of this projection, and divide it into square of the length of the vector. And also, there are the third modification of algorithm. It's algorithm with partial correction. You see that the distance from the point to the object plane is equal to projection divided by the length of the vector. It means, I mean, this value. And if the new point is chosen of the plane normal at the distance proportional to this value, then we need to define the factor gamma greater than 0, thus that it's I see some noise. Sorry, I just need to check microphones. So we may estimate value C in some to select some coefficient between 0 and 2, which produce us more accurate estimation of the weight vector. And when this coefficient equal to 0, the weight vector does not change its position completely at all. And when this correction is equal to 1, that vector transfer to a new position situated directly on the object plane. So it will be object plane, it will be this, yes, this direction. And when it's equal to 2, the weighted point moves to the other side from the plane at a distance equal to the initial distance between W and the plane, as shown here. So this situation when our value is equal to 2, yes. And in this case, you see that this correction a little bit too, maybe a little bit extreme. Yes, you don't need to pass your weight vectors far away from your object plane. So you may select a value between 1 and 2, and it will be enough. And the learning algorithm with error correction generally comprises a sequential test of a set of object planes. The task for each plane is to find out whether the weight point lies on the proper side. And if the position is wrong, the weight point travels transversely toward the plane. The process goes on until the separating weight vector is obtained as shown in the figure here. It provides the theory that all three algorithms converge in infinite number of steps. So we assume, and it was defined in mathematical way that we will have finite number of steps if our objects, if our two groups has linear separability. We may find this position. So it's example in the right part for four objects. So we have first hyperplane for our object, and we just move our vector from some initial randomly initialized vector to, yes.
Sorry, is it the surface plane that is moving or the
Could you just really poor quality of voice?
you cannot hear me well?
Not well, not very well.
Okay, let me type it then.
Let's try one more time.
Can you hear me now?
Yes, it's better.
Okay, what I was saying is it the weight vector that is moving or the plane itself, the hyperplane? So
Unfortunately, I could not understand the question one more time.
it was the weight vector that we were changing to adapt to the. I don't know if you can go to the previous
Really
slide.
difficult. Could you maybe write the question? Weight vector moving, only weight vector. Plane corresponds to the object. So it's like an object plane. It's every time it's perpendicular to our object. It's not a separation surface as in case of Fisher discriminant analysis. It's objects plane which divides the whole space into part with where projection is positive and negative. And if we project our weight vector to this plane, we obtain 0. So if our weight vector, we just move our weight vector. And this for cases means that we have 4 objects actually. So it's like an information about a perceptron algorithm when we recalculate our weight vector in order to find the best position where all our projections will be positive. But don't forget that we need to add additional column with ones and multiply our second class to -1 in order to prepare our data set for future analysis. This algorithm is also a linear classification algorithm, and it allowed us to work with all data sets without assumption that we have normal distribution. As you may see, we don't calculate here mean value, standard deviation, and also something like this. So it's non-parametric, and if you have strange classes, like, I don't know, with different covariance matrices, but you know that these two classes has some line, straight line, which may separate them. You may calculate, you may find this line using perceptron. So as a result of these steps, you obtain some final weight vector, and only after that you may find these separation surface. For example, your weight vector will be like, I don't know, this. Yes, and your separation surface will be perpendicular to this weight vector. In this case, yes, you may find it, but it should correspond to the final version of your weight vector. Okay, so the next part of the lecture will be about errors, because every time we create some classification algorithm, some regression algorithm, we need to estimate quality of the obtained model, and it means that we need to estimate and calculate our errors. We will talk about classification problem and about errors that occurs in classification tasks. As you know, in a regular situation, we may plot something like this. We have some value x. It can be, for example, output of of Fisher discriminant analysis, like a projection of our classes, and we have some function from this x, which gives us some value. And let's consider the simplest problem of making a decision on a random input value x, which belongs to class 1 or 2. Omega 1 is objects from the class 1, and omega 2 is objects from the class 2. We assume that we are aware of random value x, distribution densities for each class. So it's a distribution of value x. And we know that we have function 1 for all objects from the first class, some distribution, and distribution of elements f2 for all x from the class 2. So we have two distributions for two groups. They may be non-equal because you have different groups of, for example, two groups of human, you need to classify them. And you have also a priori probabilities P for classes 1 and 2, that classes 1 and 2 will appear in the classifier input. So you have probabilities for classes also a priori, so it's known probabilities. Sorry. That you have in your input class 1 or 2. For example, your class 1 and class 2 may be male and female. So you are trying to define gender, yes. And for example, you have more female patients than males. So it means that probability that input value will be from the class 1 female class will be higher than probability, then input value will be from the male class. And the solution involves definition an optimal, in a certain sense, threshold value x0, such as if x is less than x0, we adopt a hypothesis 1 that's x belonging to class 1, omega 1, and if x greater than x0, then our threshold, we take the hypothesis 2 that our object corresponds to class omega 2. So you see that we divide our decision plane into 2 parts, and this threshold allowed us to classify objects into 2 classes. You see that you have some problems that our distributions intersect in this middle zone. So you will have some errors of classification. You see this, we have 2 parts, 2 areas, area alpha and beta, which you will see that if your object x will be in this part, we assume hypothesis 2 that this class corresponds to this object corresponds to the second class, but some objects from the first class lies in this area too, and we will have some errors of classification. The same with the left part, you see this area beta. All objects from this area will be classified as class 1 in accordance with our decision rule, but some of them are from original class number 2. So we will classify this object wrong. So they have original class 2, but we assume that they have class 1. The first alpha area called the first type error or false alarm, and value of this error is equal to area under the curve, so it's like a integral value in accordance with you may calculate it if you know the distribution. So if an object from class 1, omega 1, is produced at the input, the probability of taking a wrong decision called the first type error. So you may calculate the probability of false alarm in this case, and it will be first type error. And if we are talking about second type error or target missing, so our target is the second class, and first class here is no target. Yes, and with the object from omega-2 class acting at the inputs and hypothesis 1 chosen, the second type error is equal to area under the second curve here. Yes, you see this field area. It will be second type error, target missing. But we will continue a little bit with these two types of errors, but it's not really common in use now because it's really difficult to calculate this distribution if you have small amount of data set, because all these densities it's experienced it calculated experimentally. If you have small data set, it's impossible to reconstruct these densities. And first type error and second type error is like there are some additional variants to estimate errors. It calls confusion matrix. You calculate 4 values: number of true positive observations, false negative, false positive, and true negative. What does it mean? If you have real class positive or class 2 in our case, and assigned class is also 2, it means that you estimate your target correctly. It's true positive value. You calculate number of these values of this you calculate number of objects from the second class which were classified correctly. It will be your true positive value. The same with the true negative value. You have negative class 1 or 0. It depends on just how did you call your classes. The negative will be number of objects from the first class which were classified as first class. So it will be true negative. And now you need to estimate false positive and false negative. False positive is a number of objects from the first class which were classified as second class. And if we back to the definition, you will see that it's first type error. Actually, no, it's errors of the first type. It's our false alarm. So false positive, and if you say that someone has a cancer when this patient doesn't have a cancer. False negative, if you have real class 2, but your classifier said that you have class 1. Number of these errors will give you false negative. And using these 4 numbers, you may calculate several statistics which reflect quality of your model. The most popular is accuracy. Accuracy calculated as number of true positive and true negative objects. So it's all objects, number of objects which were classified correctly from the first and the second class. And you divide it to total number of observation. Actually, this is general number of objects in data set. So if you have 100 objects, and from all these objects, 93 were corrected, were classified correctly. It means that your accuracy will be equal to 93%, or 0.93 is equal. Specificity is also popular in medicine, and so sensitivity in medicine also popular. When you take true negative values and divide it to total number of objects from the first class, and the same will be with sorry, false negative, false here should be false positive. So there are several variations. It will be false positive rate. Okay, I just write it here. In medicine, there are some specific ways to calculate efficiency of an algorithm of classification. You need to estimate sensitivity, which is equal to number of illness patients which were classified correctly, true positive, divided by true positive plus false negative. It will be, in this case, it calls recall. So and this value is equal to number of observations from the second class. And specificity is equal to total true negative divided by true negative plus false positive. It will be number of patients from the second class. What does it mean? That sensitivity of COVID test is equal to 80%, and specificity of COVID test is equal to 99%. What does it mean? It means that your test in 80% of cases detects patients with COVID. So 80% of patients with COVID will have positive test, and 99% patients without COVID will have negative test. So it reflects how good your test finds illness patients and how good your test does not find illness for healthy patients. Is it clear?
In other words, we have 100% chance of false positive, which is detecting that the patient has COVID while actually he doesn't have COVID. This is
yes, this is false positive, yes.
And 20% chance of not discovering COVID while the person has COVID.
Yes. So 20% of patients with COVID will have minus test, minus result. So in case of medicine, it's more important to estimate these parameters. And also, there are some additional parameters as precision. In our fields, it may be also like a predictive power of an algorithm. For example, you have 100 patients, and groups will be similar, 50-50. It will be class 1 and class 2. From these 50 patients, you have also some of them, for example, class 1, class 2, class 1, class 2. Sorry for my for my drawing. Class 1 will be 40, will be 10, and here will be 15, here will be 35, for example, like this. So it will be our true positive, 35. Not precision, actually, because there are a lot of variants to estimate quality of model. So you just need to take what do you want. For example, we have, in general, we have 45 patients from the second class. You see that you have here 35 and here 10 classified as second class from original group. It's our true positive plus false positive. And also, but in general, we have only 50 observations from, sorry, we need to estimate how many objects from the first class were classified correctly. So we need to divide it, this one plus 10. True positive divided by true positive by false positive. Which part of positive results is correct? So it means that I take my calculator. 45 divided by 45. That's 77% of patients with positive COVID test had COVID. So you see that in the first example, we may also calculate here sensitivity. Sensitivity here will be true positive, 45, divided by 50. Number of patients from the second class. It will be 35 divided by 50, 0.7, 70%. So you see that visible difference between explanation. 77% of positive COVID tests were correct, and 70% of patients with COVID had positive test. So it's like a variance how to represent results, and you see that you have some different ways to prepare your report about your vaccine or some decision making algorithm in order to get better numbers, highest numbers. So it's like a cheating a little bit. So next time when you see extremely efficient way to estimate some disease, just find information about sensitivity, specificity, and predictive power of this algorithm. And after that, you may make some conclusion, because in case of COVID tests, sensitivity is really, really low, but specificity is quite high. So it's really impossible to get positive test for healthy people. But it's really common when patient with COVID has negative test. But of course, it depends not only on test itself, but also it depends on procedure of taking their material from the nose or mouth, and also it depends if patients drank some water before test making. So it's not only the system problem. So, and also some errors more meaningful for us, but some errors doesn't cost anything. So let's introduce a concept of the decision cost. And even under the assumption of correct decisions having no cost, which is generally not the case, recognition errors, in our case in medicine, will lead to certain losses, probably dissimilar at different errors. So sometimes for us more important to detect some disease, and when we missed our target, for example, patient with cancer, cancer is really meaningful to detect, we will have high cost of error. If the first step error cost will be C12, it's a combination of class number 1 and hypothesis 2. So it's when we have real class 1, but we predict 2. And it will be risk corresponding the hypothesis 2. And this is our losses we will get in average per one solution if there is always class 1 at the input. So you have input of all objects will be from class 1, we will obtain these losses like an average per one solution. And the same will be for C21. Let's suppose that probability that's in our classifier input patient or object from class 1 and will be equal to pi. It means that the probability that we will have object from class 2 will be 1 minus p. Then the average risk or average losses at the making decision will be this probability that object from class 1 occurs in the input of classifier multiplied by the risk and multiplied by first type error, and plus the same but for the second type error. And the value of threshold value of x0 is supposed to be the best of the all possible values if it minimizes the average risk. In order to find these separation points, we just take the first derivative of the x0 and set it to the 0. So you remember that the first derivative will be equal to 0 for all function extremums, also for maximum and for the minimum. And we obtain this value. This we just take, we need to calculate minimum value of the risk with the sum x0. Yes, we take derivative and we it should be equal to 0. We solve this equation and it called we determine new parameter likelihood ratio, and at the results the average cost will be minimal if x0 is chosen in such a way that our likelihood ratio is equal to probability multiplied by cost divided by this of the first type error divided by this risk for the second type error. And if both distributions are normal, It means that distribution expressed by normal distribution. And μ1 is greater than m2. So we may calculate x0. Where is it? Where is it? So it will be this expression with known probabilities and known decision costs. So it's like some way to calculate thresholds automatically. But as you may understand, probability should be known a priori. And also we need to define costs, which is not the simplest problem. So it's really rare when some threshold calculates such a way. The most popular way to select thresholds, make some experiments and estimate obtained errors in terms of false positive, false negative, and estimates specificity and sensitivity of algorithms. Because we in real life, we don't know distribution actually and function, which allows us to approximate this distribution with good accuracy. So when our probabilities are equal to 0.5, or we have the same probability for two classes, and we have similar decision costs, our x0 will be center of the mean values. So it's also common way to estimate x0, just center between two mean values. Why not? But actually, it's really also, again, it's really rare when you have symmetrical distributions. So that's all for today. Don't worry that you have errors in your calculations, but you need to understand, is it critical for your algorithm or not? Because when we are talking, for example, about QRS complex detection, when you work with ECG signal and you try to detect complexes, you may have some errors, of course, but when you have, for example, 300,000 of complexes per day, and you have 99% of, I don't know, sensitivity, and it means that you will lose how many complexes? One moment. It will be 1% of complexes will be missing, and it's 3,000 of complexes. Yes, so 3,000 is quite bad. So it's really bad situation. What does it mean? It means that for this type of algorithm required something like 99.99% of sensitivity. Yes. So you need to develop something like this.
Is this quite possible?
Yes, it's possible. And but really a fun story. Now I'm working on comparison between. We are trying to develop some procedure to compare results of of detection via our program. In my other job, I'm working with Holter monitors, you know. So we have some program for doctors which detect complexes, and some years ago, estimated accuracy was 99%. for some signal, for quite clear signal. For noisy signals, it will be, of course, worse, but not total. And now we are trying to analyze procedure of accuracy estimation. It's like in Russian, it names GOST, or some standard for algorithms, general standard for everyone. It's like a document. You need to compare your algorithm with using some standardized databases from with the ECG records and some reference, and you need to compare your results with some reference marks. But in this standard, there is no information about minimum accuracy of your algorithm. So you just have to compare your results with the reference marks. But if you obtain results, for example, 80%, it doesn't mean anything. So just you, yes, you have checked your program for this standard, but that's all. So it's really fun. And what does it mean is the conclusion. When you develop an algorithm, just analyze which accuracy will be enough for you, and don't try to improve your algorithm selecting more complicated model. Sometimes simplest models, like an Fisher, like a logistic regression, will be better than some neural network, because a neural network is black box, and you could not explain the results of calculations. So this is some information. I just want you to fix in your memory this idea about true positive, true negative, false negative, and false positive values. Okay, that's.
I have a question.
Yes.
You said when we want to calculate the threshold for two classes, we can just take the mean, that if they have a normal distribution. So my question is, what if?
Sorry. What if what?
What if we have about three or more classes? How do we calculate the threshold?
You just need to take. If you have 3 classes, you have 3 peaks. Yes, in your distribution, and you select 2 thresholds. That's all. Yes.
When we select thresholds.
Also, you may take mean value of, if you have, yes, between them. I will show you one moment.
I'd like to see it because it's one of the problems we're having in Lab 5.
I will try to visualize it here. You have 1, 2, 3, yes? You have M1, mu1, mu2, mu3. So you need to define the middle between this. So it will be, I don't know, A and B. And you need to compare your X. If it's, your decision rules will be like this. So it will be first class, Fx lies between A and B. The second class, X is greater than B. So you estimate your A and B like M1 plus M2 divided by 2. Something like this. And the same for B. So this explanation is okay for you?
Very. Thank you.
You're welcome. Any other questions?